Good evening, everyone. So today we will see some problems based on power electronics devices, and we will see the polarity and conduction direction of the devices. And we will mostly talk about those frequent devices which appears in gate exam, like thyristors, power MOSFETs, power BJTs, and IGBTs. So there are various problems that has been asked in gate. So we will see one by one. So let's start the session. So the first problem I am taking, which was asked in GATE 2003. So in the problem, a MOSFET is given here, and we need to identify the polarity of blocking and the direction of its conduction. So we need to find an option, appropriate option, and then we need to conclude it. So uh, in this MOSFET, it is also mentioned that this MOSFET has an integral body diode. It means with the help of this body diode, it can conduct the way of diode is arranged in PN junction mode. So here we can see this is P, this is N. So in this direction, current will definitely flow, and the by default direction of source current that is flowing from the drain side. So the by default direction of that current is indicated here. We need to take this as a reference direction of the current. So first of all, with the visibility of body diode, we can identify that current will definitely flow in negative direction. So this on negative x-axis, it will definitely be crossed. Okay, and as we know that either MOSFETs or BJT or IGBTs, they block the positive voltage if you supply across drain to source. So if we see from the graph, the typical characteristics of power transistors are they block positive voltage and they are unidirectional devices. It means they have the characteristics in a way such that the current will flow from drain to source or collector to emitter in BJT or in IGBTs. So uh, they will definitely flow in uh, this direction, and they will block polarity of positive voltage. So here from this figure, uh, we can say that if this body diode would not have been present in the circuit, okay, so it would have blocked the this positive voltage. But now, since this body diode is there, it means its conduction direction will be bidirectional. So we have to see the first option where both the direction of currents are present. So uh, only figure C and figure B satisfy the condition that it is bidirectional, and the other characteristics, it has to satisfy that it needs to block the positive voltage, right? So only figure B is satisfying that condition, so we can pick this option, and this would be the correct option. uh, I hope this problem would be fine. Moving ahead with another problem that was asked in gate 2004. In this problem, it is mentioned that uh, the power BJT has a control switch by biasing it in cutoff region and or in saturation region in on state for the BJT, which condition will satisfy? So the option A was both the base emitter and base collector junctions are reverse biased. So first of all, to operate any switches or any power transistors as a switch, it, its base emitter and its base collector junctions both should be forward biased, okay, so that it can operate as a switch, right? And it will operate in saturation mode. So for switching operation, I'm writing it here. Both base emitter, we know that any transistors has two PN junctions, right? So both the junctions must be forward biased. So for example, I am drawing a NPN transistor here, NPN. So this is a typical signal transistor, but if we want to add, uh, if you want to operate it as a powered device, we need to add another layer of PN junction that will be a drift region, and this drift region will help in making it as a power device so that it can endure the high level of voltage and currents. So it will be typically in the form of NPNP like that. So let me draw it for you. The first N region would be heavily doped with electrons, and second would be P. The third layer, which I was talking about, this is a drift layer, which enables the device to endure more currents and which will allow the device to current, which will allow the device to operate at higher level of power. So like that. So we need to forward bias both the terminals. So uh, this option D, that is recommending that both the base emitter and base collector junctions are forward biased. So that is satisfying our option. So this is also true for IGBT as well. So now moving ahead with another problem. So this problem was also asked in GATE 2004. It is related to MOSFET, and no characteristics of MOSFET is given. Here it is implied that MOSFET is rated for 15 ampere of current and it carries a periodic current as shown in figure. In the figure, we can see that this MOSFET is conducting for half of the time period in one cycle, and its on-state resistance is also given, that is 0.15 ohm, and the average on-state loss in the MOSFET we need to evaluate. So first thing is that MOSFET is a majority carrier device, and during on condition, MOSFET is modeled as a resistor only, right? So why we are calling it a majority carrier device? So basically, the conduction happens because of only either electron or holes. Okay, there will be scenario no, there will not be any scenario where both the holes and electrons are moving and conducting. So generally in BJTs and IGBTs, they are known as minority carrier devices because there are two PN-PN junctions. So holes traverse from its P junction to N junction and electrons traverse from its N junction to P junction. So that condition does not satisfy in power MOSFET. So generally in power MOSFETs, what happens? Uh, Gate signal, we have control from gate signal and it creates a channel, and by the channel, if it is a N type MOS, so it will create an N type channel, and through that channel the conduction will take place. We will see in later session that how that thing is working. First, if we will be done with these problems, then it would be easier for us to understand those topics. So, right. So, MOSFET is generally modeled as R-on, and if we need to find out the loss in MOSFET, so we need to treat it as as a register, and we can easily apply this formula IRMS square into R, right? So R is given, the waveform of current is also given. We just need to find out the RMS value of this current that we will do, and then we will choose the appropriate option. So for IRMS, let me find it in one time period, then square into dt from 0 to pi, and it is convenient to take it in d omega t since we are dealing in angular terms, and we will get it eventually n by root 2, right? So it will come out to be 10 by root 2, that is 7.07 ampere of RMS current it is flowing, and if we square it, so we will get 7.5 watts. So power loss is 7.07 ampere into square into R on was 0.15 ohm. So it will be 7.5 ampere. So option C would be correct. Right. So moving ahead with another problem. This problem was asked in GATE 2005, that uh, we need to identify the curve of conduction loss in power MOSFET versus its device current, right? So now only we saw that its current or any power MOSFET is modeled as R on, right? And power loss formula, we saw that IRMS square into R. And if we try to find out, see, R is fixed, right? And its loss is depending on current. So we know the square of, we know the graph of a square term, y is equal to x square. This will be k into x square. So if we plot it, so it will be like a parabola, right? So we can choose the option of parabola because it will be nothing but the RMS square, which is nothing but the square of a term, a particular term. So it follows y is equal to kx square, right? And this is the curve of y is equal to kx square, a typical curve of parabola. So we need we needed to pick the option A of parabola. So it was pretty easy problem. Right? So moving ahead with another switch realization problem, which was asked in the same year, 2005. This switch is required to block voltage of either polarity, okay, during its off state, as shown in the figure, right? Does this statement mean? This statement means that it should block both the polarity of voltages, right? So we need to pick the devices out of these four options, which will block the both polarities of voltages, and this switch is further required to conduct in only one direction, right? So from these two sentences, we can identify the requirement of our switch is bipolar, blocking capability, and unidirectional current flow. Okay. So some switches out of these four options are not a standard. So actually these some switches are made up of combination of two or three switches. So that we can see here. So we will move from option A, like first switch is thyristor. So thyristor, it has the characteristics that it blocks both the polarity, right? It has two conditions. First is forward blocking mode, another is reverse blocking mode. Okay, it will conduct in one direction, that is unidirectional, and it will conduct only if we provide a gate pulse, right? So it satisfies the both condition, and hence the first thyristor will be correct. We will see the second switch. It is an IGBT connected with an anti-parallel diode. So this anti-parallel diode will enable this device to conduct in both directions, right? So it will be a bidirectional switch. Okay. Now the third one, and it will be unipolar as well because this IGBT will block the positive voltage, right? It will block the positive voltage, and this positive voltage will be blocked by this diode as well. So it will be unipolar and bidirectional switch. So we will eliminate this option. Now the third option, it has an IGBT or BJT is in series with an inverted diode. Okay. So what does it say? So let's assume positive polarity across all these devices. So if we assume this kind of polarity is there, then this IGBT will block it, and this diode will also block it. Okay. Now this IGBT will allow to flow the current in this direction from right to left, but this diode, it will not allow the flow of current from one to one dash, right? So uh, in this switch, no current can flow because this diode is connected in series with inverted polarity. So, mm, however, it it will block a positive voltage and it cannot block negative voltage. Let us see what will happen if we apply negative voltage. So, if we apply negative voltage, this BJT will not block this kind of polarity, as well as this diode will also not block this kind of polarity because diode will also be forward biased and BJT will also be forward biased. So this option will also get eliminated. The fourth option, that is and BJT is connected with a diode in series and an anti-parallel diode. So here, first let us see what will happen if we apply positive polarity of voltage. So this IGBT will block this polarity, right? But this diode, which is connected in series, that will not block, right? So they will not block this polarity, and this switch or this anti-parallel diode will enable the switch to conduct in both the direction. Okay, so it is a bidirectional switch and it is an unipolar it has unipolar blocking capability. Okay, so it is also eliminated. I think we did one mistake in option R, that is it can block, right? How it will happen, that doesn't matter, but it can block both the polarity of voltages, but at the same time it can flow either from this direction or this direction, right? So that is also wrong. So I think only P would satisfy the condition. So option A would be correct. Okay. So that we need to carefully analyze the situation. We need to apply step by step the polarity of voltages, and we need to visualize the direction of current step by step so that we will be able to see the characteristics of switches. So that was all about it. One more problem uh, that is based on power loss in switches. Uh, It was also asked in 2005. So we need to find out the energy during turn on transition or a turn off transition, right? What is the energy lost during these transitions? So from here, so generally power is what? VI, right? And energy could be, power is nothing but the energy per unit time or work per unit time. So we can write VI into dt, okay, from 0 to t. Now, we will consider this instance as 0 and this as a t1, okay, just for the sake of simplicity. And we will integrate for this period and we will again integrate for t2 period. From for t1 period, which transition is happening? So uh, here voltage has some magnitude, but current is rising. Okay, so switch is getting turned on, right? Or for second transition, voltage is coming back to zero, and current has reached this duration. So during this duration, the switch is in on condition, and during this condition, the transition of current is happening, and in second time, the transition of voltage is happening. Okay, so we can integrate, and here voltage is constant for T1, right? So energy we can write as from 0 to T1. Okay, V is constant, I is rising with slope T, so I into T by T1 I into dt I dt, right? So after integrating it, we will get Vi into T1. And during on transition, we will again calculate it from 0 to T2. We will take the same condition. It was for off. It is for on 0 to T2. This time voltage is varying with time. Okay. And okay. In E into dt, I dt, right? Hmm. So basically, we cannot write it as a straight away I dt as I into T1. So what would be preferable here? I dt is nothing but the area of this curve, right? So we can calculate its area. So we will take V from 0 to T1 into I dt, and the area of its is uh, area of triangle. So half into I into T1. So it will be Vi into T1 by 2, because I and T are two different identities, so we cannot straight away write it as I dt is equal to IT. And second thing, here we will do the same thing. Here current is constant and again VDT. So we will again need to calculate the area of this curve, and that will be I, sorry, this will be capital I into half into V into T2. So Vi into T2 by 2. Now this is the energy for energy loss during on condition, and first one was energy lost during off condition, and we need to compute both the energies. So E total is E on plus E off, that is nothing but Vi into T1 plus T2 by 2. Okay, I hope this would be fine. Now moving ahead with another problem. This was again asked in GATE 2005. Okay. So in this problem, a BJT, power BJT is connected in series with a diode, and we have to assume that transistor and diodes both are ideal, and we need to identify the correct IV characteristics. Okay. So again, a very simple problem, right? So uh, we will again apply both type of polarities of voltage. So let us assume when positive voltage was applied across both the terminals. So this IGBT will block positive voltage. Okay. However, this diode will block negative voltage, right? So it is satisfying the criteria of bipolar blocking capability. And we can see from the direction of switches that this NPN transistor will flow the current from its collector to emitter, and its diode will have the direction of current from P to N. So it will allow the current to flow in positive direction. However, for negative direction of current, both transistor and diode will block this direction of current. So it will not be allowed in this switch. So unidirectional current flow. Okay. Now we have to pick the options appropriately. So which options uh, has this condition satisfying? So I guess bipolar blocking. So this C option satisfying bipolar and unidirectional. So C option is correct. Bipolar and a unidirectional. So C is correct. Yeah. So yeah, this was all about previous year problems related to power electronics devices. We can see one more problem, I guess, based on these devices. So let me take it. In this question, it was asked in 2009. Okay. So in this problem, we have to match the suitable IV characteristics of the devices. So first is a simple PN diode. So it will block negative voltage, and A will be negative blocking, right? Negative blocking and positive flow of current, right? Positive current. So this is satisfying option 4, right? So A will have option 4. Let me write it here. It is having option 4. Now B is a thyristor, so it blocks both the polarity of voltage and it conducts in positive direction. So from option 3, we can see it has bipolar and unidirectional similar to thyristor characteristics. So we can write B for option 3. Now C is nothing but an IGBT. So an IGBT blocks positive voltage and it conducts in positive direction. So that is satisfying option 1. So for C, it will be 1. And D, again, an IGBT is in connection with an anti-parallel diode. So it will allow the flow of current in both the direction. However, it will block only positive voltage. So that is satisfied by option 2. So, and whichever the option is satisfying all those criteria, uh, those will have the correct option. So for A, it is 4. So in which A is 4 in C and D. Okay. And for B, 3 again in C and D. Now C is connected to 1 in option C only, right? So we can say it from here that C is gonna be our final option. However, we need to cross verify with option D, and D has connection with 2, so C is our final correct answer, right? So I hope you must have got proper idea of how the switches conduct in which mode. So those are all basics about switches. Now we will see some characteristics of the devices like BJT and MOSFETs. So, yeah, so first we will see power BJT. That is nothing but similar to a signal transistor of BJT, but a slight change will occur. That is the introduction of a drift layer. So let us take an NPN, which is generally used. So NPN type of power BJT. So here plus identifies or plus denotes that it is heavily doped, and minus denotes that it is a lightly doped region. So N will have electrons and P will have the holes, and this first N plus is heavily doped, and that is nothing but your emitter. It is base, which which is known as control signal for any power BJT transistors, and this drift region is introduced in between base to collector, and this one is collector, right? This is base. So uh, the current which flow from collector to emitter, that will be responsible for the active power or the identification of the rating of the device, and the base current, it will be responsible to control the switch, whether our switch should be in on condition or off condition. So let me also draw a BJT. So this is VCC, EB, and this emitter terminal. So here the current that will flow to emitter, this is the uh, notation of current is flowing from P base to N emitter. So this is one PN diode and this is one PN diode. So we know that BJT is made up of two PN junction diode basically, and whatever the current that is coming from collector, that will be enabled by this base signal, and hence this emitter current will comprise of both the currents, that is IB. If VV signal will be activated, some current will flow, all right, because it is a current controlled device. So if VV will be applied, so some current will flow, and that current will be added to the collector current. So that's why I is known as IC plus IB. And further, if we see the characteristics of this device, so let me draw the characteristics of this device. So first of all, for working it as a switch, it must operate in saturation mode. So what does I mean by saturation mode of operation that we will see here? First, we will draw the input characteristics of this switch. Right? So what does I mean by input characteristics? So input means our input terminal is VBE, right? This is input side and this is output side. Let me show you a full picture. So from output side, we can say if we draw the characteristics of or graph of VCE versus IC, that will be output characteristics. And if we draw the waveform of VBE versus IB, that will be input characteristics. And IC is related with IB, that function is nothing but the beta. So IC is generally related with IB with beta. So however, this does not hold true in saturation region. The reason behind it I will explain in a moment. So first let me draw the its characteristics. Okay. So it is a PN junction, right? Base to emitter is a PN junction diode typically. So it will have some threshold voltage. So its characteristics of IB with respect to VBE will be something like this. This will be some threshold voltage, right? However, it will also depend on VCE. VCE will be third parameter or Z-axis parameter that I am going to identify it. So what will happen if we change the VCE? Okay, that we need to identify from the circuit here. So let's say apply a KVL here. VC is this voltage. VCE minus VBE is equal to ICRL. Okay, this is RL. Now IC is also related to IB, so we can write beta IB into RL. So as you increase this VCE, right, then sorry, VC minus VB equal to ICR, right? So as you increase VCE, your IB is gonna decrease. So if you plot with different VC, let's suppose a lower value of VCE, right? Um, these two blue curves have lower value compared to first. So for this condition, or for similar IB or similar base current, okay, your VCE is decreasing, right? You plot it, so your VCE is going to decrease a bit. It will not affect much, but that's the thing. If you increase VCE or if you decrease VCE, your base current will increase. So yeah, your base current is also dependent of the output parameter, but not by much amount of the value. So this is the input characteristics, and now we can see the output characteristics. Yeah, one more thing. Why we called it as a saturation? Okay, that will be cleared in output characteristics. So output characteristics will have VCE, sorry, it is correct, VCE versus IC. And this third parameter will be IB. Okay, this is how IB is increasing, then we can see that IC is also increasing, right? So this IB, let us assume IB1, IB2,
IB.
IB3. So as base current is increasing, collector current will increase. And this region is known as saturation region. Okay. In this region only we need to operate our switches. However, this region seems to be an linear region, but this is not so because we are not seeing the full picture. If IC is equal to beta IB, and if this curve is linear, then we can say that it is a linear, right? IB, IC. If this curve is like that, then we can say it is a linear region. But after some point, it doesn't matter how much we increase the base current, your collector current is not gonna increase. So that will be fixed. So that's why it is known as linear region. And during this region, it's happening. And we are here seeing in output characteristics the relation between VC and IC, not IC and IB. So that's the one thing. And its value VC threshold, we should not try to uh, cross this limit of threshold. Otherwise, you will be fall in active region. And after, if you go further, you will be in breakdown region. So that's all about its output characteristics, I guess.
Hello, sir.
So I have drawn a curve also of,
Hello, sir.
let me bring it here.
Hello, sir. Sir. Hello, sir.
Yeah. So here you see, as
So
you
you have
apply
a
VB,
question from
base voltage,
someone.
your base current will rise, right? But for turning off, it will take some particular time, and your VC,
Hello,
the
sir.
voltage of collector, VC and AC denotion of that saturation, right? So it denotes that it is operating in saturation region, and your voltage will fall from this level, from rated to some zero. For ideal, it will be zero, but it's most of the switches will not be ideal, right? So it will be just above the zero, just near to zero, some 0.4, 0.7 volt, and your current will rise, and this is the transition, right? This is transient kind of thing. And after that, from this period, from this point to this point, particularly this point, it will conduct. And as soon as we give the negative signal of voltage,
Hello, sir.
this base current will also try to reverse its direction. However, the collector current will take some time to follow, and it takes lot more time compared to other high frequency
Hello, sir.
devices.
What topic you teach, sir?
Because we know that BJT is, it has low frequency. It is known as low frequency device. It means it takes lot of time
Hello.
to get turned on and turn off. That's why it will take some time to
Hello, repeat.
fall below its limit when all the charges. that were stored in
Can you say
P
which
and N
topic?
junction
Uh,
that
it's switching
will be
characteristics of
recombined
the
or
devices.
depleted,
Yeah,
then
okay,
it will be
thanks.
in turn off condition, and again your voltage will rise. So total this much time it will take for turn off, and here also it is taking some finite time for getting turned on. So it is uh so and that's why it is known as a low frequency device. So that's what I wanted to discuss about it. I hope this should be clear.
Yes, sir.
Anyone is speaking, I am not able to hear anyone. Again, I think I have some issue with my earphone. Okay, I can see the message, so it is fine. Thanks.
Okay, sir.
Oh, yes, Nokiti, you are right. I am not audible. Sorry, you are not audible to me. I think again the same issue.
Hello, sir.
Okay, anyway, we will carry on. Let me just switch the device. It is
Hello,
offline
Ricky.
device.
Hello, sir. It's not audible, sir.
I think sir is fixing his devices. So
No, sir. I understand, sir.
yes, sir. I was actually getting confused in when they are blocking forward voltage and all of these concepts. Yes, sir. Yes, sir.
Sir. Hello, sir. Sir, can you show the question, sir? I'm not visible. It is very small letter, sir. Yeah, yes. It's now visible, sir. Okay, sir.
No, sir. Clear.
No, sir. Now I clear, sir.
Sir, isn't it the last session for this phase two? So, if you are free, then otherwise I'll study on my own. Yes, sir. Yes, sir.
Hello, sir. Sir, this is an property of the power MOSFET, sir. The formula is any the for formula is there for power MOSFET any formula, sir? Okay, that one. Okay, sir. Okay, sir.
Yes, sir. From all the previous question, the basic concept is clear. So I think we can attempt questions on this topic. Yes, sir. So in Wednesday's sessions are told us that this will be the last session. So I thought you knew. Thank you, sir.
Thank you, sir.
Yes, sir. Your sessions were interacting as well.
I was very clearly understanding the basics, sir. Thanks for that, sir. I was clearly understanding the basic concept of MOSFET and power of MOSFET, sir. So thank you, sir. Yeah.
Thank you,
Thank
sir.
you, sir.